We're continuing with L'Hopital's rule, and there's one more method that we need to talk about that applies to L'Hopital's rule. Most of the time, this method applies when you have something raised to a power, like maybe you would have 0 to the infinity or infinity to the 0, something like that. Both of those are called indeterminate forms, which means you got to do something to get it in the form of L'Hopital's rule. So here's an example. If I plug in infinity, I get infinity and then 1 over infinity. Well, I know 1 over infinity, that means the bottom's getting bigger and bigger and bigger, so that's infinity to the 0. I don't know what that means, but there's a method that you can use to solve it. So what you do, it's a strange process involving natural logs. What you do is you set this equation equal to y. So y equals the limit of what we're looking for. Well, then you take the natural log of y. If you take the natural log of one side, you have to take the natural log of the other side. Now, the good thing about natural logs is that whenever you have a natural log of something, the power can come like in front, or you can bring that power down. So this becomes natural log. Actually, what you can do with the limit and natural log is you sort of can switch them. If you're taking the natural log of the limit, you can put the limit outside, so that's what I'm going to do. I'm going to make it easier to see. So natural log of x, and then when I bring down this 1 over x, I'm like timesing the ln of x times 1 over x. Basically, I'm just putting it over x. So now, when you plug in infinity, you get infinity over infinity. Ta-da, you can use L'Hopital's rule. So L'Hopital's rule says that we take the derivative, 1 over x. We're still approaching infinity. 1 over infinity is 0. But 0 is not the answer. We've got ln of y equals 0. And then so now you solve for y. Remember there's an e right there. So e to the 0 equals y, which means y equals 1. And so 1 is the limit of that problem. Alright, so this one, if I plug in 0, I get 0 to the 0. It's another strange thing. Seems like it should be 0 or 1 or something, but we don't really know. So what we're going to do is we're going to do this process that we have just talked about. So we're going to say natural log of y equals, and take the natural log on this side as well. And again, I'm just going to go ahead and move my natural log inside of there just to make it easier. Now, I've got to do something with the sign, so I want it to come down in front, just like I said that you could do with natural logs. Anytime you have natural logs, the power can come down in front of the fraction. I still don't really know how to solve this, but the way we do sometimes whenever you have things multiplied, you can, remember, bring it to the bottom by making it 1 over that. So now when I plug in 0, I get ln of 0, which is negative infinity. On the bottom, it's 1 over 0, which is infinity. So I've got a big number and a big number. We don't know what that means, but I do know that I can use L'Hopital's rule. So the derivative of ln of x is 1 over x. The derivative of 1 over sine x, think of it as sine of x to the negative 1, so the derivative would be negative sine of x to the negative 2 times the derivative of the inside, which is cosine of x. Now that looks pretty complicated. I'll tell you, if you start plugging in 0 right here, you get something like infinity over 0 or something like that. But this looks so complicated, so what I'm going to do next is I'm going to simplify. So I'm going to make it 1 over x over negative cosine of x over sine of x squared, which I'm going to simplify again. It's the same as 1 over x times and flip it. So that makes x times sine of x squared over negative cosine of x. You know what? That x is not on the top. That is on the bottom with the negative, or with the cosine, because it's 1 over x. Alright, when I plug in 0, I do get 0 over 0 now. So guess what? We get to do L'Hopital's rule again. Yippee! Now, I'll tell you that if you start doing L'Hopital's rule, you're going to get something kind of complicated with the derivative. It may or may not work if you continue to do it. But there is something else to do, and I know this problem is really yucky, but I just wanted to show it to you as one of the times that it might be difficult. I think the others I have to show you are not quite so difficult. It's actually not going to work if you do L'Hopital's rule again. So I want to simplify this a little bit more, and it doesn't look like it can be simplified more, but that's a sine of x squared over cosine of x. What I can do is I can leave the x on the bottom, and sine of x over cosine of x is tangent, and so what I can do is I can just rewrite that as tangent, and then there's an extra sine of x, so all of that is on the top. If you plug in 0, you still get 0 over 0, so I am going to do L'Hopital's rule at this point. It may have worked up here, but it probably was a little more complicated. So I'm going to do the product rule first, times the derivative of the second, plus the second times the derivative of the first, which is 1 over cosine squared over negative 1. Tangent of 0 is 0. Cosine of 0 is 1. This is 0. Sine of 0 is 0. Cosine squared of 0 is 1. So we've got 0 plus 0 over negative 1. We get 0. That is not the answer because we still have this ln at the beginning of the problem. So ln of y equals 0, which means y equals 1. Alright, if I plug in 0 here, I get e to the 0, 1 plus 0, so this is 0 to the 1 over 0 infinity. So I know that I need to do something else. I'm going to rewrite it with a natural log on both sides. And I know I'm going to bring that down, so I'm just going to go ahead and do that at the same time. Times 1 over x or over x. The ln's on the top with that. Alright, if I plug in 0, I'm going to get 0 over 0. So let's do L'Hopital's rule. The derivative of ln of something is 1 over the something times the derivative of the something. So there's an e to the x plus 1 on the top. And then over 1, because the derivative of x is 1. Plug in 0, e to the 0 plus 1 over e to the 0 plus 0. So that's 1 plus 1, which is 2 over 1. You get 2. So natural log of y is 2. See, I told you, this one wasn't near as bad as the last one. Alright, limit as x approaches 0 of x to the x. So that's 0 to the 0. So we're going to do natural log equals the limit as x approaches 0 of x, natural log of x. It's not in a form of L'Hopital's rule, so we're going to rewrite it as natural log of x over 1 over x. Plug in 0, you get infinity over infinity. Check. Let's use L'Hopital's rule. Derivative of the top is 1 over x. The derivative of the bottom, that's x to the negative 1, so this would be negative x to the negative 2. And then we're going to simplify before we do anything, since I know that some of those x's can go away. Negative x to the negative 2 is the same as negative 1 over x squared. So I can rewrite that as negative x squared over 1. We get negative x. Plug in 0. You get 0. So natural log of y equals 0, which means y equals 1. Lots of zeros and lots of ones here. Last one, this one's not really like the others because it sort of is already in a good form, but I'm just going to go ahead and do it while I'm here. Plug in infinity, you get ln of infinity, which is infinity, and the ln of infinity is infinity over infinity. You can go ahead and take the derivative. The derivative of natural log of something is 1 over the something times the derivative of the something. And then over 1. Plug in infinity. So we've got 0, 1 over infinity, times 0, which is 0. I want to give you some hints on that 24 through 28, just in case it's a little bit helpful to you. On 24, if you'll rewrite that as the secant is 1 over cosine, and secant squared is 1 over cosine squared of 3x. So if you'll rewrite it like that, and then 1 over x times and then flip it, I think it's easier to solve the problem from here. You'll start right there, plug in your 0, or plug in your pi over 2, and then you'll have 0 over 0, and you can do L'Hopital's rule. On 26, if you'll rewrite cosecant as 1 over sine, and cotangent as cosine over sine, and then if you get a common denominator, if you do the limit of this, you'll get something you can do with the L'Hopital's rule as well. On 27 and 28, if you'll get common denominators on those, and then create a fraction, you'll be able to use L'Hopital's rule, and that will work as well. I just thought these two with the sines and the cosines were a little bit more difficult, so I wanted to show those to you.